Okay, great. And for the last talk of this first session, we have Carlos, who's going to tell us about how he plans to besiege the black hole tower. Take it away, Carlos.
Okay, thanks, Enrico, for covering me with this problem that I have with the recording. So let me start by thanking the organizer for inviting me to give a talk in this wonderful conference. I'm going to report on an ongoing project work that I have been doing in collaboration with Julio Arrechea, Valentin Boyanov, Raúl Carballo, and Luis Garay. So let's go to the future for just a few moments. It is already year 2041, and they have been announced that the researchers have been able to produce the first radiography of a black hole. And then there you go. And then let me spend a minute to explain this graphic, this plot. It represents ultracompact object. The metric, the radial function, the R of I'm using a radial proper coordinate L to portray the geometry, and then the green line represent the form, the shape of this object, which has this asymptotically is flat, and then at some point it bends a little bit, and then it ends up in a regular R equals 0 position. And then there are three important functions. One is what is called the compactness function, which is this blue line, which represents the mass, the total mass, 2 times the total mass that is inside a specific radius of the structure divided by R. And then this compactness is such that at infinity, it goes to 0, but then it grows up to 1 point, 1 radial position, at which it reaches values very, very close to 1. In fact, they can even be precisely 1. And let me say that there are these geometries, they have two different notions of compactness. One is how close to 1 this C of R can get. And another thing is the redshift function, this other line that you see here, which in this case it's going to 1 if you want in asymptotic infinity, and then it slowly decreases, and at the position in which this object has a specific surface, and inside it is full of matter. So at the position in which the matter start to be located, this redshift function reaches values close to 0, but not quite. So this is so the difference between and this is the second compactness notion, is how close you get to have a redshift 0 surface. And then once you reach this point in the surface of the object, then you start going inwards, and the redshift function still decreases a little bit more, but it reaches the R equals 0 with a number which is still is very small number, but different from 0. So this is the and let me also explain that I didn't say before, that the compactness function, this blue line, it does in the external part of the geometry, it does this thing which is very similar with what happened with the Schwarzschild geometry. But then in the internal part, it starts to decrease inwards, and it becomes negative. It becomes negative, meaning that there is an internal region in the space-time that the total energy density of the space-time is acquiring negative values. And then it has this form, and at the end, it closes regularly at R equals 0. So it makes this shape. Okay, so this is the geometry that, as I said, this is something for the future. And then, of course, this is just a dream. So we have to go back to reality, which is in 2020, which is already quite amazing, because we have observations of black holes that were almost a dream a decade before. So Paolo did already a very nice introduction and motivation for why to look for exotic compact objects as alternatives to the black hole paradigm. And well, it is, and the studies of these things are becoming more popular these days. And if only as, I mean, if you only have to choose one motivation, you could say that it is interesting to have these models to have a backdrop in which to compare the GR predictions. All these exotic compact objects are objects that are distinct from more well-known objects like neutron stars, but still they have two additional characteristics. From the one side is that typically they are more compact than neutron stars, and on the other side they have they are naturally dark, because these two things are necessary in order that they can accommodate, they can supplant, they can mimic the observations based on the black hole paradigm. But I have to say that most of these approaches, there are several in the literature, do not discard the eventual formation of black holes. Is that, for example, when you look at boson stars, these are objects that could exist, but their existence do not enter into conflict with the existence of black holes. You could have different families of objects. Some there are boson stars, and all others there are black holes. On the contrary, the logical scheme I'm going to talk in this talk, it takes as thesis the rejection of the very existence of black holes as long-lived objects. I will explain that. So my personal besieging of the black hole tower is based on different approaches that are mixed up and they are logically connected. On the one side, and is the one that I'm going to talk today more extensively, there is this semiclassical gravity arguments based on searching for static configurations, self-consistent static configurations that are solutions of semiclassical Einstein equations. But then on the other hand, there are studies in which what you analyze is dynamical situations. How do semiclassical effects are behaving in dynamical situations? The two things are quite different in the way in which you approach the problems. Then there is another topic which I'm working on, which is this, what I call emergent gravity. And is this analysis of how viable is to have a theory of gravity emerging from condensed matter-like systems. And in this, although there is no a complete theory of emergent gravity, there are many ideas floating around. And there is, and one thing that is suggested in this framework is that gravity could switch off at very high energies at Planckian, when matter reaches Planckian densities. So this is another thing that can be entered into play. And then there is also some issues about effects based on theories in which there is superluminal dispersion effects. That also, in some situations, they also point out that they might make static horizons, objects with static horizons and regular, they can make them to be unstable or rapidly unstable. So one thing that I want also to mention is that one thing that separates quite a bit the black hole paradigm from other paradigms based on exotic compact objects, and is the reasons why a new figure of equilibrium exists, and the mechanisms that allow the formation of this object. The thing is that in the black hole paradigm, these two notions are somewhat intertwined, because the collapse process itself, with some relaxation, gives place directly to the final black hole object. Is that once the horizon is formed and starts to become relaxed, I mean, with no hair, then these objects can be understood without caring too much about what is going on inside the structure. So in some sense, the formation, as I said, the formation of the object leads directly to the final object in astrophysical terms, because whatever happened in the standard paradigm, whatever happened in the regions close to the singularity, would not affect the physics of the astrophysical way in which these objects behave. Instead, in the framework I will sketch here, and well, I would say that in most other proposals that suggest exotic compact objects, the physics that one have to understand when analyzing the equilibrium or the figures of equilibrium, how are these objects, would be rather different from the formation mechanisms. So, because typically these formation mechanisms would involve transients, quite energetic transients, in which the physics that you have to control might differ. Also, the phenomenology associated with the transients could be very different from the phenomenology associated to understand how the object itself behaves once it has been formed. So now let me pass to the central part of the talk, which is based on this semi-classical gravity approach. Well, the semi-classical gravity is the idea that the inhomogeneous zero-point energies, densities that are supposed to exist, and if you accept that they exist, it is also natural to accept that they should gravitate. In fact, it's a rather conservative idea. The idea that in gravity there are vacuum polarization effects, which are similar to what happened in other theories, like in electrodynamics. But then you have this idea that I signal here with this 0-point contribution, that this means that what you try to do with semi-classical gravity is to maintain the idea that you have an effective metric. So you are always at the scales, at effective scales at which any microscopic structure of the geometry itself is not, you are not proving that. You are just proving an effective geometry. And then what you just do is to try to control what is the average effect of this vacuum polarization additional sources of energy. So that's why I say is that the semi-classical gravity is trying to solve Einstein's equations with a classical stress energy tensor term plus some energy momentum tensor representing these 0-point fluctuations. But this is the idea. But then, of course, you want to have a precise definition of what is this with additional stress energy tensor. And the most natural point to start with is to try to extract this information from the stress energy tensor, or making this stress energy tensor an operator in the quantum theory. You have a field, you quantize this field, living in a curved background, and then you try to see whether the expectation value of the stress energy tensor operator is something that you can use as a source for the equations of these semi-classicalized equations. But the problem is that the stress energy tensor and other objects, other quantum objects, is not a directly well-defined operator in the quantum theory. And it's because it involves the product of different fields at the same point. And then this, so in order to really extract information to that, you have to recourse to, you have to involve a regularization and a renormalization procedure in order to obtain this renormalized stress energy tensor. As is well known, this process leaves certain ambiguities based on the form of the form of the regularization and renormalization process that you follow. There is also very hard calculation difficulties depending on the approach, and there are also other problems, like other conceptual problems too. In some approaches, there is these runaway solutions, so there are things that one have to solve. But in any case, even notwithstanding these problems, semi-classical gravity already shows certain potentialities, which are very nice to probe. On the one hand, it has been known for a long time that these additional terms, these semi-classical terms, provide energy condition violations in certain situations. And for example, it is well known, for example, in the Hawking effect, that the presence of this evaporation is the possibility of evaporating a black hole horizon is precisely because the stress energy tensor at the horizon itself is violating energy conditions of GR. But more than that, it has been also proved that these violations can become large in certain situations. So it's not that even though the semi-classical effects are always multiplied by the Planck constant, there are a quantum effect, this could be thought as something that only can change the classical behavior only slightly, because you add to a stress energy tensor, which is classical, some quantum stress energy tensor, which can be very, very small. But it has been proved that this is not completely correct. The thing is that this smallness of the Planck constant, or the Planck length, can be counteracted by the behavior of the geometry itself in certain situations. Typically, when horizons are very close to appear, when you have configurations that are close to forming horizons. Another thing that that semi-classical gravity allows is that, for example, when you analyze spherically symmetric stellar-like configurations, you can have that the total energy density, which is composed by the classical term plus the semi-classical term, can develop regions in radial segments within the star, in which this quantity increases outwards, even though the classical part is just decreasing or is not increasing. This is also a peculiar characteristic of semi-classical gravity. And in addition, they can also introduce, they directly, in most typical situations, they introduce anisotropic pressures. Even if the classical energy momentum tensor is, you take it to be with isotropic pressures, then the addition of the two tensors, of these two sources, it leads to anisotropic pressures. So all of those characteristics work against the Buchdahl compactness limit, meaning that one can suspect that by analyzing this semi-classical gravity, you might have configurations that surpassing the compactness limits of Buchdahl. So in order to progress in these semiclassical ideas, I mean, there are different approaches, but I think that one approach which for us it has been proved to be very interesting is to use the Polyakov approximation for the stress energy tensor. The thing is that this Polyakov approximation, which is very well known, is a qualitative approximation, which has a good compromise between precision, well, qualitative precision, I would say, and manageability. Because what happens is that there are more precise forms of stress energy tensors, but are difficult to use for analyzing self-consistent solutions of these equations. So this Polyakov approximation is, first of all, it's nice because it's unique. It has only second derivatives and it's analytic. So it can be used directly for analyzing self-consistent solutions of the semiclassical equations. And here you have, well, physically, what this Polyakov approximation, it represents the not only it takes only into account the S-wave contributions of the fluctuations, and it neglects the existence of backscattering in the geometry. So you have here the form, well, the essential form of this of the Polyakov approximation. But the Polyakov approximation has also a problem, and you can see here in this highlight green, and it has a divergence at r equals 0 when you use it in 3+1 configurations. That's why it is not, it does not allow to analyze regular stellar configurations. One needs, the first thing you have to do is to regularize this r equals 0 divergence. And the simplest way to do that is to add a cutoff here with this parameter alpha. And then what we call the regularized Polyakov approximation is precisely that, is you add a cutoff to the standard piece, and then you have to add some angular additional components in order to make the entire stress energy tensor to be conserved. So the thing is that what we have done is to take this, this stress energy tensor and use it to find self-consistent solutions to spherically symmetric and static configurations. And the first thing we did is to find the vacuum solutions of the geometry, what is meaning the Schwarzschild counterpart in the semiclassical gravity. So these are the solutions in which you don't consider the existence of matter. The stress energy tensor of classical matter, you put it to 0. And then what happened is that when you analyze this solution, the Schwarzschild solution is transformed into a wormhole solution, which has this form. It's an asymmetric wormhole. The compactness function, this blue line, reaches 1 in one particular place, which is now the neck of the wormhole. And at the same position, the spreadsheet function is different from 0. So that's why it avoids the presence of a horizon. But then this wormhole is quite strange because it's asymmetric, and in the internal region, it develops a singularity, which in this approximation is located at a radial position, which is finite, but the radial coordinate at this position is infinite. So it's a, but I mean, it's a non-regular solution, but it's the solution that you have to use in order to then find solutions with matter, because the external part of the geometry has to be a piece of this geometry. And then what you do is you take from the asymptotic infinity, you take this solution up to a specific point, radial point position, and at that point, you put matter. And then you integrate the equations from here on, you integrate the equations with a matter content. And in order to do that, the simplest matter content that one can think of is this constant density star, in which you leave you leave matter, well, you leave pressure to do whatever it needs to do in order to be a solution, a self-consistent solution of the equations of motion. And then, well, in this paper that Julio Arrechea, which is part of his thesis, it shows all the solutions that all these systems of equations resolves. But here I want to show the specific form of some solutions in which what you have is something that is very close to the dreaming image that I put in my first slides, with only one difference, is that you have something which is very close to that, but when it reaches, when it goes to radial positions which are very close to zero, then it sort of turns its behavior and becomes a wormhole. And these wormhole throats can be as small as you want. So the thing is that these solutions are very close to these regular solutions that I was suggesting, except for the behavior of the geometry in a central core that can be made quite small in comparison with the total radius of the configuration. And and what I want to stress, this is probably the main point, the most important point in this talk, is that there is a complete different behavior of the classical and semi-classical equations when trying to build a SuperBuchdahl configuration, meaning a ultracompact object, something in which the surface of the object is very close to where a horizon would be formed. What happens is that when you analyze that at the classical level, you have that you start with a configuration which has a specific radius and a specific mass, which is very compact. And then you integrate inwards. So what happened is, and you integrate inwards with a parameter that in principle you don't know what it is, which is this density, the density of the star. The thing is that when you change this parameter, by changing this parameter, you can make the compactness function to be sort of regular in a central core. I mean, what you need is that the compactness, when you are in close to the central core, it's very small because it has to match with C equals 0 at R equals 0. So you have a window, this blue window in which this happens. But then you also need that the pressure is regular at this same core. The thing is that this can happen, but the pressure, the window in which the pressure behaves appropriately is here. So it does not coincide. The window at which you can more or less control the compactness function does not coincide with the window at which you can control the pressure. So there is no way the solutions, the SuperBuchdahl classical solutions, are very, very far from being regular. They are very irregular configurations, and that's why the typical assertion is that they are not existing. I mean, that general relativity do not allow these configurations. Instead, when you integrate the semi-classical equations, what you have is that the two windows, the window in which you control the value of the compactness and the places in which the pressure is under control, they coincide in a central core. So we have found what can be called quasi-strictly regular configurations, and they are quasi-strict only because at the end of the day, in R equals 0, they really, in the final stages of the radial coordinate, they blow up. They go for these wormhole solutions. So the remaining questions is, can more refined versions of the renormalized stress energy tensor, which have a better behavior at R equals 0, regularize this course? And we have preliminary analysis along these lines, and they point into the affirmative. But we have also been able already to show that by just leaving some freedom to the regularizing function of the Polyakov approximation, you can already find some regular solutions. It would be nice also to know whether these solutions are stable. Once you find a solution, a completely strictly regular solutions, is to find whether these solutions are stable or not. Right now, we cannot say almost anything about that. We have this intuition that is only based in the fact that when you make the configuration more compact, then the semi-classical terms are becoming more negative, and then it might be the case that they compensate for reaching stability. So I think I should start finishing.
I think probably that's a good idea. If you're close to, yeah, should wrap up. Yeah.
Okay, I have a few things more, but I was passing just to suggest that one thing I was saying before is that one thing is to have equations to find specific solutions which are self-consistent, and another thing is to analyze how do you get to these solutions. And the formation mechanism for these things is something that has to be analyzed separately. And well, in the discussion section, if someone is interested, I will sketch this. So summary and conclusions is that well, there are strong evidences that vacuum polarization effects can support ultra-compact stellar-like configurations. And using this cutoff regularized Polyakov approximation, we have found quasi-regular SuperBuchdahl configurations. As I said, again, I already said that the formation mechanisms and the equilibrium figures is two different things. And then, of course, just to say that that many analyses remain to be able to assert the complete viability of this scenario. But the motivation, I would say, that is stronger than ever. So thank you very much.
Wonderful. Thank you very much, Carlos. So let's go to, maybe we can take one question. So we are running a little bit behind in time. Let's take, I think I saw what was one question in the audience. So Cheyu, I given you the mic. Go ahead.
Hi, thank you. So thank you for the talk. So I just have one question about the regularization. So in that slide, you have additional parameter alpha. Is that arbitrary, or can it be fixed by some equation of motion?
No, this alpha is arbitrary, and we have analyzed how it affects the solutions. In fact, when you take this alpha has to be greater than 1, strictly greater than 1. And then what we analyze is how the solutions are affected by this parameter. So the thing is that when alpha tends to infinity, you recover the classical solutions. And when alpha goes to well, start to be comparable to 1, is when you are putting, you highlight the semi-classical effects.
Okay, thank you.
Okay, so any other questions? Okay, so I guess it's probably then a good time to take a break.